kids, welcome to Unit 9. Look what I saw at my church this weekend. Whoa, imagine that. Just as I'm about to start teaching vectors and parametric equations at my church, they're preaching vectors and parametric equations. Anywho, the big idea of what we're going to do here with vectors and parametrics is we're going to take equations that we know, for instance, I don't know, x squared plus 7. And this is what we call a two-variable equation because we have an independent and a dependent. And my independent is a single variable. And my dependent value just depends on what I do to that single independent variable. Well, I'm going to talk about a function like this, breaking it up into more than one piece. And I'm going to use vectors and parametrics to do that. It's kind of a way of getting more variables, multivariable, into a single variable equation. And by single variable, I mean single independent. All right, but before we do any of that, we got to go over some basic operations and terminology with vectors. All right. A vector is an ordered pair of real numbers. There's lots of different notations that go with vectors, but oftentimes the pointy brackets, where A goes with a horizontal piece or component and B is the vertical component. For example, here's my two-dimensional plane, x comma y. There's what looks like a normal line, right? A regular old line starting at the origin. But this is the tail of the vector, and this is the tip of the vector, and the tail right now is at the origin. And I am kind of pointing in a positive, a horizontal and vertical direction. So here is my horizontal, and there is my vertical component, and that would land me here, in this case, at the tip. Sometimes you'll see a little arrow over the notation for vector. So the component form does look like this. And again, sometimes you see it like this. Sometimes you just see the V bolded. But at component form, if it tells you the horizontal and vertical component, the assumption is that the tail is at the origin. Or I can just give you any vector. It doesn't have to be at the origin. I could click and drag this here. Given that the length of this vector and this vector are the same, and that I know my drawing is kind of poor, but they're going in the same direction, vector 1 and vector 2 are equal. Because it has the same length and direction. We can talk about the 0 vector. Not very interesting. Its components are 0, 0, so its tip and tail are at the origin. Yawn. Again, equal vectors either have the same components, well, duh, or they have the same magnitude and direction. So that's the power in vectors. You can click and drag a vector and put it, as long as you maintain its magnitude or its length and its direction, you can move it anywhere. To be in component form, though, you would need to have the tail at the origin. So vector 2 and vector 1 may be equal, but they might have different, they would have, this would have, let's say that's point P. And this is point at the tip is point Q. Same length, same direction, but This vector 2 is not in component form because its tail is not at the origin. So when we have just one dimension, right, not on the xy plane, we just have a one dimension, we call that a scalar. And just think of a scalar as some kind of number, right? And examples of scalars, right, the length of something, right? Even the area, I know you think of that as area is units are squared, but it's still just a number, right? The area is 5 units squared. The volume is 17 units cubed. The temperature is 72 degrees Fahrenheit, right? The speed is 50 miles per hour. Those are all scalars. Vectors are velocity, acceleration, displacement, direction, force. Because vectors, and you might think, you've probably heard of speed and velocity being the same, sort of. What a vector has, scalars might have a length, yes, might have some kind of number associated with it, but vectors have that number and direction. So I might be traveling 50 miles per hour, that's my speed, but my velocity is 50 miles per hour east, 50 miles per hour north, right? That kind of thing. So how do I take a vector that I want to be in component form that wasn't given to me in component form, right? Component form is I don't have to have, but it is the easiest to manipulate with. So if I am given some point here at the tail and at the tip, I call that vector, see how this is bolded? I call that vector AB, so I indicate to you which is the tail and which is the tip. If I want that in component form, I just subtract. And you subtract head minus tail. So if I want to transform AB to the origin, which means I would put it in component form, I would get that. So for example, I'm going to give you a vector RS. So R is at the point R is negative 2010. And the point S is 0, 0. But that's RS. So who's the head and who's the tail? R is the tail. So RS looks like that. That's not in component form, right? Component form has the tail at the origin. So how do I get RS into component form? Zero minus negative 20 and 0 minus 10. -20, -10. Those two vectors are equal. They have the same magnitude. I'm sorry, they're not equal. One's in component form. Yes, equal. They have the same direction. Oh, what am I talking about, right? Same magnitude, same direction. They are the same. Oh, I certainly would want that. Now, so I did that. Now, find the point Q so that RS and PQ are equivalent. Well, again, what does it mean to be equivalent? Either the same components or the same magnitude and direction. So haven't done anything with magnitude yet, so let's try to get the same components. So is P the head or the tail? P is the tail. So 3, 4 is the tail. I need it to be the same length as red and purple and the same direction. And I have to find Q. How are you going to do that? Well, since this is a tail, this is x1, y1. Q is x2, y2, right? What do I want x2 minus x1 to equal? What do I want it to equal? 20. How about, right, y2? y2 minus 4, what do I want that to be equal to? -10. So when I do that, I get 23, -6. Let's check our work. If I claim this is 23, -6, can you put PQ into component form? Well, that would be 23 minus 3 and -6 minus 4. Oh, snap. PQ and RS have the same components, therefore they must be equal. Woot! Let's talk about the magnitude and direction. Come on in, hun. Come on in. Couldn't be a unit without Pythagoras somewhere. There he is. I mean, he's just all over the place. The magnitude of a vector is its length. Hello? Right? Think about the first drawing I did. Oh, I probably have drawn this again, but whatever. If this is vector AB, the horizontal component was A. That's the change in X. Here's the change in Y. That's the vertical component, which we called B. How do you find the length of the hypotenuse? It is the square root of the side squared, sum of the side squareds, OMG. I did draw it, see that? So magnitude, Pythagoras. This is, right, denoted, right, because it's not taking, you're going to get a positive number, right, by Pythagoras. Magnitude is length. Length is positive. Now, here is the angle, theta, that my vector makes with the positive x-axis. So that's standard position. The direction angle of a vector is the angle whose cosine is what? Cosine is adjacent over hypotenuse, right? Well, remember what this side, here's the adjacent side, here's the hypotenuse. But the hypotenuse is a length. There's the magnitude. And the sine is the opposite over the hypotenuse. Well, what's the opposite? The vertical component. So the direction angle What's the tangent of the direction angle? Tangent is sine over cosine. So B over the magnitude. What happened? Bye-bye. So you can take the inverse tangent, but you have to be very careful about what quadrant you're in. Right, so you can adjust, because you know when you use your calculator and get inverse tangent, it's going to either give you an angle in the first or fourth quadrant. So what if I want you to find the magnitude and direction of vector 4, 8? So it's in component form. So you know the tail is at the origin and the tip is at 4, 8. So the magnitude is just Pythagoras. What is that? 64, 10, 6, 7, 8. Square root of 80. Yes, you can simplify that if you want. And the direction. So I'm in quadrant 1. Inverse tangent of the vertical over the horizontal. Inverse tangent of 2, which I get on my calculator. And nobody gave me an indication of whether I should be in degrees or radians. I have to say most often these problems are done in degrees. And I got 63.4-ish. Okay. Magnitude, direction. What if I give you the magnitude and direction? Can you find the components? So can you go backwards? So if I want to know, there's the horizontal component. How are you going to get that if I give you the magnitude and I give you the angle? Well, there's the vertical component. There's Pythagoras. Gotta love them. And what did I write here? This blue length, right? This length, using Pythagoras and my triangle trig, isn't it true that the cosine of that angle is the adjacent over the hypotenuse? Therefore, the adjacent side is equal to the hypotenuse times cosine of theta. Well, what is my hypotenuse? And there's cosine theta. Can you do the same thing for sine? I mean, for the vertical component? I think so. So if you know the magnitude and direction of a vector, you can get the component form of the vector. Try it with this one. You might want to pause the video. Notice that I am in degrees here, so put your calculator in degrees if you haven't already. Although 120 is a special angle, so you really shouldn't need your calculator. Yeah, sorry. So magnitude of 52, and with the positive 120 degrees means this is the vector I'm looking for in component form, right? So my tail is at the origin. So the magnitude is 52. cosine of 120 degrees, and 52 sine 120 degrees. Cosine of 120, you know what that is, right? -1/2. Sine of 120 is √3/2. Right? I'll use my calculator, and I got 45-ish. Oh, something, can't read my writing. Does that make sense? That your tail, what quadrant are you in? -26 up to 45. That's reasonable. All right, vector addition and scalar multiplication. Resultant is a vocabulary word you should have in your notes, and it means the result of combining two vectors. So if I have two vectors in component form, I just can add their components. So if I take vector u, add vector v, put them tip to tail, the resultant vector connects the tail of the first to the tip of the second. I can also, of course, subtraction is just addition of the opposite. So if I take vector v and add its opposite, which is just a scalar multiplication of v by -1, so it is the same direction, opposite direction, same length. That's u plus -v. Goes from the tail of the first to the tip of the second. The scalar multiplication of a vector is like the dilation factor, right? So if you have a scalar of a vector, you just multiply that scalar times each of the components. So there's vector u. There's vector k times u, where k is a number bigger than 1, positive number bigger than 1, right? You see that? So has the same tail, but is, almost twice as long, maybe a little bit more. Here is vector u with a scalar that is smaller than 1, but still positive. So maybe that's 2/3 u, where k is 2/3 maybe. There's vector u, and there is where k is negative, and maybe it's even just -1, right? So not only do these operations, but tell me what you're going to get. And without actually doing them, hopefully you can see 2 times a vector. This is still going to be a vector, right? The magnitude, order of operations. What am I going to do here? I'm taking the magnitude. I only know how to take the magnitude of a vector. So what's inside is a vector, right? 3 times u, vector u, is a vector, minus vector v, still a vector. What happens when you take the magnitude of a vector, though? The magnitude of a vector is a scalar. What's going on here? Well, let's see. This is a vector, right? Vector v plus twice vector u. So I have one vector in here. And then what are you multiplying by? A scalar, right? The magnitude of vector v is a scalar. So that's just, what are you going to end up with? A scalar times a vector is a vector. Okay, so I'll leave you to practice those. I'll tell you what I got. Hopefully this one, you can see -6. 12 is what I got here. For this one, I got 9. This is a scalar, I got 9. And for this one, I got a vector. I got -√45 times 11. And √45 times 10. I didn't bother multiplying that out, as you can tell. Okay. All right. So I just did some drawings there. Here's U, here's V. So hopefully you can see 2 times V, negative 3, 6. What that would look like would be negative 6, 12 up here, so on and so forth. Come on, pen. Froze up on me. There we go. All right, a unit vector. Think of your unit circle. A unit vector is a vector with a magnitude of 1. So let's suppose that I have this blue vector. Here's the light blue vector. Gosh darn it. The light blue vector has a length of 2.5. What if I don't want it to be a length of 2.5? I want the unit vector representation of that. I want to shrink 2.5 times vector A to just vector A. How do I do that? I divide by its magnitude. So if I have a magnitude of 2.5, I take vector A and divide it by its magnitude, and I have the unit vector. You have the same direction angle, but you have a magnitude of 1. So you're not equal, right? We're not talking equal vectors here. So there's the IB notation for a vector. And if I ask you to find the unit vector, that means find the magnitude, then divide each component by the magnitude. So there is negative 5, 12. That does not have a length of 1. What does it have a length of? Square, right? 25 plus 144, square root of. Here is my unit vector. My original vector divided by its magnitude. Remember the square, this is a scalar. That is a nice Pythagorean triple. 5, 12, 13. So my unit vector is negative 5 thirteenths and 12 thirteenths. Same direction, tail at the origin, but scaled back. So unit vectors, because again, remember, vectors are used often to show direction and magnitude. Often the direction is really important, right? I kind of deal with the length later. So if I have a whole bunch of vectors describing, I don't know, the magnetic field of the earth maybe, right? I might want to know, right? I don't want all the vectors and all their lengths. It's too much for my eyes to interpret. But what if I have just a bunch of unit vectors describing the magnetic fields around the earth? Kind of cool. Oh, more orthogonal. Oh my goodness, aren't we so fancy? Orthogonal unit vectors, I and J, alphabetical order, just like X and Y is in alphabetical order. So some pretty famous unit vectors are the unit vectors representing the vector 1, 0 and the vector 0, 1. What is the magnitude of this, right? This vector's magnitude is automatically 1, right? And here they are, 1, 0 and 0, 1. They are the unit vectors along the positive X and positive Y axis. What that means, using the idea of resultant vectors, I can write any vectors in a linear combination of just I and J. So look at this drawing here, vector A. What if I said vector A is not a result of adding vector X and vector Y? Truth? Right? You can see that, right? Because vector X, whoops, why did I do that? is 1, 0 plus 0, 1 is equal to 1, 1. That is not vector A. However, what if I told you that there was some scalar times each one of those that did equal vector A? Right? So that's the idea behind a linear combination of unit vectors. So this is a little bit nicer. If you have AB, right? The tip is at AB. I can write that as a linear combination of my unit vectors. Because after all, what is A times 1, 0? That's just A0 plus 0B. What's that resultant vector? Right? But 1, 0 is I and 0, 1 is J. Here is my linear combination of unit vectors, is a way to represent vector A, right? Resultant vector. So what if I want you to express this vector? Let's pretend that vector A, this is in component form, so the tail is at 53.2. Oops, sorry. So express that in terms of unit vectors means a linear combination. Combination with adding I and J. (53.2) times the unit vector 1, 0 plus 127.8 times the unit vector 0, 1 lets me write that vector as a linear combination, and there's lots of math I know how to do with linear combinations. OMG! All right. Oh my gosh, look at all this information. Find the unit vector in the direction of u, -3, 2. Can you picture where that is? Did I draw it? No, I didn't draw it. So, vector u is at -3, 2. There's vector u. Find the unit vector and its direction. So maybe you want to pause the video and do that. And then I also want the answer in component form, and I want the answer in a linear combination with I and J, and I want the angle of direction, OMG. Here's the angle of direction. The unit vector is going to be in the same direction with the same, right? So the same angle of direction, but have a magnitude of 1. They want me to write the answer in component form, and they want me to write the answer as a linear combination of I and J. All right. So again, maybe you want to pause the video and do this and then check back, or do it with me here. That's going to go here. Don't know why I wrote it over there. What is, how can I write that in as a linear combination? Copy and paste. Done and done. What's the only thing I haven't done? Right. Inverse tangent of y over x. That never changes. What quadrant am I in, by the way? Quadrant 2. So be careful when you get this answer from your calculator, right? You're going to get something in quadrant 4, so you're going to need to add 180 to it. And I can read this. I got 146.31. So there's my angle of direction, which makes sense in quadrant 2. Here is the component form of my unit vector, which is that purple vector right there. And here is the linear combination that gets me this purple vector as a result of horizontal component, vertical component. Each one times 1, 0, and 0, 1. All right, that's it for now. We will do some more of this in our next live session.